In the last class, I have started discussing stability analysis. Stability analysis. So in case of stability analysis, first I defined classically allowed region and classically forbidden region. Classically allowed region. Classically allowed region are those regions where kinetic energy of the particle is greater than or equal to किससे ज़्यादा होगा बेटा? That will be zero. Or you can say, in another words, total energy is greater than or equal to potential energy. Second, classically forbidden regions where kinetic energy is less than zero or negative, or this total energy is less than potential energy. Total energy is less than potential energy. So in this way, we have defined classically allowed region and classically forbidden region. In case of classically allowed region, if this is the case, then two situations may arise here. Either particle will be at rest. Particle will be at rest if kinetic energy is zero. And if particle is having kinetic energy greater than zero, then it will be in motion. It will undergoing motion. Okay? It will undergo motion, and here kinetic energy will be greater than zero. Now, two type of motion we are going to study. One is bound motion. That will be bound motion. And second is unbound motion. So in case of a bound motion, particle will undergo, okay, oscillatory motion, true and true oscillatory motion about a stable equilibrium point, and within this motion will be bounded by the two turning points. So here, in case of bounded motion, basically two turning points are needed. So two turning points are must. Two turning points are needed, are must for the bound motion. So here, if motion is taking place in between two turning points, then that will be a bound motion. And it will be an oscillatory motion. So here, bound motion, I have discussed bound motion in the last class with the help of spring mass system. Yes, beta, please.
The previous slide.
Okay. Is it okay? Can I go to next?
Sir. Yes, sir.
1 second.
हेलो सर सर अगर ये सरफेस अगर फ्रिक्शन लेस नहीं हो तो मतलब उस कंडीशन में भी मोशन ऑसिलेटरी होगा क्योंकि लगातार एनर्जी लॉस होगा। सर मैं ये कह रहा हूँ, हेलो सर।
यस बेटा।
मैं ये कह रहा हूँ सर, अगर जो सरफेस है वो अगर फ्रिक्शन लेस ना हो तो उस कंडीशन में भी क्या अपना मोशन ऑसिलेटरी होगा? क्योंकि
it will be oscillatory, but damped oscillations will take place. System is going to continuously lose energy, so slowly amplitude is going to decrease. Or you can say turning points, they will continue to move towards the equilibrium point. Okay? Oscillatory motion will be there, but damped oscillations will take place.
जो allowed region है वो continuously मतलब reduce करेगा।
बिल्कुल. That is going to continuously reduce because allowed region that is dependent upon the energy of the particle. Because
Okay,
energy is reducing, automatically that is going to reduce.
Okay, sir.
So in case of bound motion, ठीक है, in case of bound motion, there will be a true and fro motion, true and fro motion, fro motion around stable equilibrium point, around stable equilibrium point, equilibrium point, and within two turning points, and within, or you can say, and between, and between two turning points. Turning points. So when I will discuss, I will draw the phase trajectory, I will give you many examples of the bound motion. We will find out many examples of bound motion as well as unbound motion. So we were here in the last class. Okay, we were here in the last class. Now, next is unbound motion, beta. Next is unbound motion here. Unbound motion. Unbound motion. Best example of the unbound motion to understand unbound motion is scattering problem. Is scattering problem. Problem. Scattering problem, basic problem you can choose. Suppose alpha particle scattering I can choose. Suppose this is a nuclei. Okay. This is a nuclei plus ZD. It is carrying a positive charge plus ZD. And if you launch an alpha particle towards it, so what you are doing, you are launching an alpha particle. So an alpha particle is launched here. So what will happen? You will observe that this alpha particle will move like this toward the alpha particle, toward this nuclei, and then it is going to move like this, in this way. So here you can observe that this motion, this alpha particle is moving towards the nuclei, and because it is carrying positive charge here, this nuclei is also carrying positive charge. So when there will be a electrostatic interaction between them, then there will be a repulsive interaction. And as a result, it will be, this alpha particle will be scattered in this direction. So this is one of the best example of the unbound motion. So this is a physical example of this. I will explain you how this happens, how it can. So try to understand first, when you are launching this, you are launching this alpha particle with some velocity. So it is having a kinetic energy. Kinetic energy, you can say K alpha. That will be 1 by 2 m alpha V alpha square. M alpha V alpha square. Right now, when you are launching the alpha particle, it is very far away from the nuclei, and we assume that the interaction between the alpha particle and nuclei is negligible. So here, at this position of launch, you are saying potential energy is zero. Potential energy is zero. Now what happens? Yes,
सर
beta. Yes.
सर जब हम सर इस तरह के न्यूक्लियर रिएक्शंस मतलब करते हैं सर, फॉर
Okay.
एग्जांपल प्लस जेडी न्यूक्लियर, यहाँ पे सर जो उस न्यूक्लियर का जो एटम है उस पे तो इलेक्ट्रॉन्स भी होगा, उन सबको रिमूव किया जाता है या डायरेक्ट एटम पे ही मतलब वो अल्फा पार्टिकल को स्ट्राइक किया जाता है?
It will be actually जैसे you are going to have a foil, ठीक है ना? So foil में क्या होगा बेटा? Electrons they are very lighter particle. First understand this, ठीक है ना? They are very very lighter particle. Second, most of the space in an atom, ठीक है ना? That is empty. So that's why when this type of interaction you are considering, you are neglecting the interaction of this alpha particle with this electron, with the electrons, because chances of that interaction will be very small, because space most of the space of the atom, that will be empty. So here, if you look at, electrons will be here. ठीक है, electrons will be here. And this nuclei is concentrated in a very small, this is kitna hoga, this will be of the order of 10 to the minus 15, and here size of the atom, it will be of the angstrom. So you can understand this space, more or less this space is empty. Most of the mass is focused here, and most of the charge, positive charge, that is concentrated here. Why electronic charge, if you are considering, that is distributed around it. So interaction, main interaction will be in between the alpha particle and this nuclei. ठीक है? Is it clear what I'm saying? So
Yes, sir.
mean
Yes, sir.
interaction will be in between alpha particle and the nuclei. ठीक है? That's why you will find out that most of the many of the alpha particle, or a significant percentage of the alpha particle, they will move unscattered like this. ठीक है? The reason is this space is more or less empty, and size of the electrons is very, very small. So come back.
So it is
So
same
he,
with all type of nuclear reaction ना सर?
yes, beta.
मतलब
This,
हर
yes,
एक न्यूक्लियर रिएक्शन के लिए
yes.
सिमिलर ही होगा ना सर केस?
Different type of reactions are there, but I'm talking about right now alpha scattering problem. ठीक
ओके
है?
सर.
I'm talking about, yes, beta.
Because the nucleus mass is large and the space is most of empty.
More space is more or less empty. First thing, if you look at electron, they are distributed, they are surrounding the nuclei, so they are spread in the complete space. Why? Here most of the mass of the atom is focused here in a very small tiny space. Okay, that is nuclei. So you can consider that the interaction of this alpha particle will be mostly with this. So if it will be affected, its direction will be affected, that can be affected by this nuclei itself. If it is interacting with the nuclei, that interaction will not have the ability to change the direction, or to for this scattering problem. So that don't have that capability, because mass of this alpha particle is very, very large as compared to the mass of the electron. If you consider this alpha, this will be alpha nuclei, 2He4 nuclei is this. So 2 protons plus 2 neutrons will be there. Okay? And mass of the proton or mass of the neutron, okay, na, that is roughly 1836 times mass of the electron. So you can consider that this alpha particle is very, very heavy as compared to the electrons. So if you are considering this type of interaction between electron and the alpha particle, that doesn't have the ability to scatter the alpha particle significantly. So they are not responsible for this
Sir,
scattering.
but
Yes,
this is
beta.
the sir Coulomb interaction ना sir?
Yes,
Electromagnetic interaction.
this is Coulomb interaction,
In
electrostatic
yeah,
interaction.
yeah, in electromagnetic interaction, where is the mass transfer? It is like Q1 Q2 by R by into 1 by 4 by epsilon naught.
Yes. Yes, that will be there. What will be the potential energy here? Potential energy will be 1 upon 4 pi. I am unable to understand the question actually. 1 upon 4 pi epsilon naught. How much charge this is carrying? This will be plus 2E. This will be potential energy plus ZE, and that will divided by R. This will be. So what is the question basically? Here?
Sir, you said something related to mass of the electron is very less, like that.
Yes. Mass of the electron is very less as compared to the mass of the alpha particle. So due to this, if interaction between electron and alpha particle is taking place, this interaction will not be able to it will not be able to basically change the direction of the alpha particle very significantly. I'm saying this. ठीक है? So
Okay,
here,
sir.
so come back. Actually, my objective was something else here. ठीक है? For unbound motion, basically best example of the unbound motion was the scattering problem. So what type of scattering here? alpha particle is interacting with this nuclei and it is scattered away. If you look here, okay, it is interacting, it is coming, it is interacting and then gone. It is not going to come back and interact with this nuclei again. Try to understand. It is interacting with this and it is moving away. Now it will not come back. So there is nothing like bound state here. So this type of this is called as scattering problem, where a particle is coming, it is interacting here, and after interaction it moved away forever, forever. So this type of problem, they are called as scattering problems. In these scattering problem, unbound motion is there. This particle will not remain bound with this nuclei. It is not going to interact with it again. It one time interaction will take place and then it will move away. Then it is going to move away. If you look at this problem here, potential energy is how much? You can say this will be K. You can say Q1. Q1 is suppose the charge of the alpha particle, Q2 suppose charge of the nuclei, and this will be R. This will be R. Okay? So here potential, how potential is varying? Potential is varying as 1 by R. So here potential is varying as 1 by R. 1 by R. Okay? And try to understand one more thing here. Here, try to understand that if you look at this alpha particle here, its motion is towards the, if you look here, it is towards the nuclei. But after this point, if you look at, its motion is away from the nuclei. So direction of motion is changing. So first it was moving toward the nuclei and then it is moving away from the nuclei. So here, after this point, it is scattered. Its direction of motion is changed. Its direction of motion is changed. So this type of problem, they are coming under the preview of this unbound motion. How it happens, how this takes place, it will take
Can you
place
show
like
previous
this.
slide?
Just 1 second. Just 1 second. So if I plot this potential here as a function of R, so what is the potential here? Here potential is which is varying as 1 by R. So here potential is varying as 1 by R. So on this side, I'm having energy. I can have energy, or I can have potential energy if required. Another type of energies may be there. This is 0 here. So if I plot this potential will be something like this. It is varying as 1 by R. It will be like this. Okay? It is like this. Now, just please note down.
Done, sir.
Okay, beta. Now, try to understand. Now you are launching what I was saying at that time here. When you are launching this alpha particle towards the nuclei, it is considered that it is very, very far away from the nuclei. So when you are saying that nuclei and this alpha particle, they are very, very far away from each other. They are very, very far away from each other. In that case, potential energy will be 0. No interaction is there, so potential energy will be 0, only kinetic energy will be 0. So there will be some total energy. And what will be the total energy? That will be kinetic energy plus potential energy. So it will be 1 by 2 m alpha v alpha square plus 0. So this is the total energy that you are providing to this alpha particle in the form of kinetic energy. Okay. So now come here. So you have provided energy equal to E to this particle. So that energy will be positive and it will be somewhere here. So this is the energy. This is the energy of alpha particle, you can say. E alpha. This is the total energy of the alpha particle. E alpha. You have provided this energy to the alpha particle. Now try to understand. Where is the turning point? Now next question is, where is the turning point? Turning point is that point at which kinetic energy is becoming equal to potential energy. and particle is reflected back by some type of restoring force. It may be repulsive force, any type of force will be there, but particle will be reflected back from the turning point. So turning point is a point where potential energy becomes equal to the total energy. वो total energy के equal हो जाएगा. Potential energy and total energy, they will become equal, and at that point particle will be at rest for a moment, and after that it will be reflected back some type of repulsive force or restoring force. So that is turning point. So where is the turning point? This is the turning point, beta. So here if you draw the perpendicular, this will be the position of turning point. This will be the position of turning point, beta. तो ये क्या है? I call it as R naught. I call it as R naught. So R equal to R naught is the turning point.
Energy is equals
Yes,
to
beta.
total energy.
Yes.
This point, the potential energy is equal to total energy.
हाँ, total energy and potential energy, they becomes equal at this point. Correct, beta. ठीक है ना? So here this is potential energy. If you look at this, this is a graph of potential energy which is varying as 1 by R. And this is the total energy, beta. You can write it as total energy of the alpha particle you have given. You can change it. If you suppose you high energy you are providing, then this line will be here. If you are providing lesser energy to the alpha particle, it will be here. Correspondingly, your turning point will move for a higher value of R or a lesser value of R. Okay? So this will be the total energy of the alpha particle, and it will be conserved. It will be
तो
conserved
ये जो
because
टर्निंग पॉइंट है इसको,
yes.
तो जो ये टर्निंग पॉइंट है ये इक्विलिब्रियम पॉइंट भी होता है ना?
इट विल बी, अभी आएंगे बेटा वहां, ठीक है ना. आई विल कम टू दैट, ठीक है ना. आई विल कम टू दैट. सो हियर आई विल शो यू दैट इट विल बी अ टर्निंग पॉइंट और नॉट. So here, this is R naught. Now what you have done, you have launched a particle. From here you are launching the particle. So when you are launching the particle, separation between this alpha particle and nuclei, this is large. So R value is large. And as it is moving towards the nuclei, R value is becoming less. So you can consider that in this way. You can say that your nuclei is here. You can consider that nuclei is somewhere here. So you can consider nuclei is placed at this point. So what I'm saying, you have launched the alpha particle from this side. Alpha particle is here. You provided it energy. Okay? You provided it energy in the form of kinetic energy K alpha. As this particle is moving towards, with this kinetic energy, it is moving towards the nuclei. Try to understand, it is moving towards the nuclei. So it will move toward the nuclei here. So continuously it is moving like this, moving like this, moving like this. And as it is moving like this, what is happening here? What is happening to this kinetic energy? When this alpha particle is moving towards the nuclei, what is happening to this kinetic energy? Kinetic energy of this alpha particle, it is decreasing. Try to understand, when it is moving
converts
in this
into
direction,
potential.
potential energy is increasing. What is happening
Yes,
when
sir.
alpha particle is approaching the nuclei? Interaction between the nuclei and the alpha particle is going to increase. As a result, this potential energy will increase. So in this journey, kinetic energy is decreasing actually. Kinetic energy of alpha particle is decreasing. And at the cost of this kinetic energy, this potential energy is going to increase.
Sir, but
Yes?
after reflection, R naught will
No,
increase.
please wait for that. Okay, I am not reached up at the point of the reflection. Okay, so this nuclei is approaching here, approaching here, approaching here, approaching here. It is approached here at this point. What will happen at this point? At this point, kinetic energy is becoming zero. Try to understand. At this point, kinetic energy is zero because potential energy is equal to the total energy. So you are saying at this point, K alpha is becoming zero, and this potential energy, it will be equal to total energy. And what was the total energy? Total energy was K alpha. This was the this will be equal to E alpha, you can say. So potential energy will become equal to E alpha.
So
E alpha.
kinetic energy convert हुई है potential
Yes, total.
energy.
This kinetic energy is totally converted into potential energy. Here, at this position, particle will be at rest for a moment, and then it will change its direction of motion. What will happen? It will be reflected back. From this point, it will be reflected back like this, and then move in this direction. And in the reverse journey, if you look at the reverse journey, here again, reverse thing is going to happen. Now, what is going to happen in the reverse journey? Now, particle is moving in this direction. So you look here, this potential energy is decreasing. So now in the reverse journey, this potential energy will go down, and kinetic energy will go up. So as this particle is moving in this direction, it is moving here at the same position, it will have same kinetic energy, but this time this kinetic energy will be in this direction, and it will move away like this. So it will move towards infinity. It is not going to come back. This alpha particle is not going to come back. So this motion, this is called an unbound motion. Here, particle is coming, interacting with this potential that is created due to this nuclei, and it will reach towards the nuclei up to a particular distance. Okay? And after that, it will be reflected back from the turning point. So this point is called as turning point.
0 to R0 region, the particles are not entered.
Yes, beta, please.
0 to R2 region, the particles are not entered.
Particle cannot enter into this region. Why?
Because
Because this is classically forbidden region. Look here.
Yes,
This is
yes,
total
classical
energy.
forbidden.
This is potential energy. So here this region is classically forbidden region. ठीक है ना? Particle cannot enter into this region. This is a classically forbidden region. And what you call this R naught? Just 1 second, beta. What you call this distance R naught? In alpha particle scattering experiment, this is called as distance of closest approach. What do you call it? Distance of closest approach. Closest approach. So what you have observed here that this scattering problem will take place when one turning point is there. Here, particle is interacting with this. It will be reflected back, but there is no turning point here on this side, which is going to stop this particle and revert back. So here only one turning point is there in case of unbound motion. Due to this region, they are reflected back. In scattering problems, there will be one turning point only. Particle is coming, interacting, reflected back, and it will be gone forever. So this type of motion, they are called as unbound motion. They are called as unbound motion. Yes, beta, please.
सर जैसे ये पार्टिकल रिफ्लेक्ट बैक होके जब अपने इनिशियल पोजीशन पे होगा तो उसका जो काइनेटिक एनर्जी है जो इनिशियल होगा सर जो था पहले जो मैक्सिमम था सर उसके जस्ट बाद अगर वो जाए पार्टिकल सर उसके जस्ट बाद जाए तो काइनेटिक एनर्जी उसका कांस्टेंट हो जाएगा सर
बिल्कुल
तो अपन
श्योरली
ये कह सकते हैं कि सर उसके जस्ट बाद
Yes, here at the
उसके अपन ये कह सकते हैं कि सर उसके बाद पार्टिकल यूनिफॉर्म मोशन गेन कर लेगा यूनिफॉर्मली चलेगा
हाँ, देखो वो try to understand what type of force is this. This is a conservative force. Electrostatic force, that is a conservative force. So kinetic energy plus potential energy, ठीक है ना, kinetic energy plus potential energy will remain constant. So when we are launching this particle, we were saying that there is no interaction between alpha particle and nuclei at this point. So we were saying potential energy was 0 here. So at this point, when it will come back, again potential energy will be 0. It is going to have only kinetic energy. So it will move in this direction. So uniform motion, you can say if it is moving with a constant velocity. If a particle is moving in a straight line with a constant velocity, then this will be a uniform motion. Okay? That will be a uniform motion. So if you are saying it is moving, no another interaction is there, nothing is there, then ideally it should move in a straight line with a constant velocity. corresponding to the K alpha kinetic energy. So in that way, you can say that this will be a uniform motion. Uniform motion means particle is moving along a straight line with a constant velocity. Direction is not changing. Magnitude of the velocity is not changing. Speed is not changing. Direction is not changing. So that type of motion is called as uniform motion. Is it clear?
Sir, in the forbidden allowed region,
Yes.
sir, the potential energy are so high, then kinetic energy becomes zero.
Yes.
Okay,
At
sir.
this point.
Yes, sir. 0 to R naught.
0 to R naught, particle cannot enter kinetic. If you are assuming particle here, kinetic energy will be negative. In this region, kinetic energy is negative because this U is greater. If you look at this curve of U, that is greater, this is total energy. So potential energy is greater than total energy. So in this region, kinetic energy will be negative if you are calculating. So particle cannot exist. Particle cannot exist with negative kinetic energy. So this is classically forbidden region.
Yes, sir.
This is
Okay,
a
sir.
classically forbidden region. Is it
Sir,
clear to everyone?
sir, uh,
Yes, beta,
hello, sir.
please.
Sir, but all particles won't reflect back, right? Some might deflect in some other direction. So
Yes.
can we say that they have a turning point also?
Actually, what happens? Try to understand. If you are launching the particle, exactly toward the nuclei, like this, if you are launching like this, then it will go up to some point and then it will be reflected back. This will be distance of closest approach. You call it as R naught. But it also depends upon on other factor like this parameter, impact parameter we call it. So if it is here, if you look here, then look at the velocity. Here velocity is towards the nuclei. Okay? Velocity is towards the nuclei, but here after this point, velocity is away from the nuclei. So basically here this scattering or reflection is taking place, but it is scattered in a different direction. So it also depends. For example, if you are launching an alpha particle from here, then interaction will be less. Try to understand. Then interaction will be less. Then it will be scattered like this. So if you look at these distances, ठीक है ना, these distances corresponding to these distances, ठीक है ना, there will be a value of u, ठीक है ना, this will be a value of u here, and correspondingly you find out the turning point. You are going to find out the turning point. Is it clear what I am saying?
Yes, sir. Thank you, sir.
So not only one thing is there, but other parameters are also playing their role, like impact parameter and some other aspects also. So basically this type of motion, they are called as unbound motion. You can write, please write here. In case of unbound motion, particle comes. In case of unbound motion, particle comes, comma, interacts with the field,
Sir, in
In-
case of unbound motion,
unbound motion. In case of unbound motion, particle comes, comma, interacts with the field, and is scattered to move away, forever. Full stop. In scattering problems, there will be only one turning point. In scattering problems, there will be only one turning point. In scattering problems, there will be only one turning point. There will be only one turning point. Next beta. Now equilibrium position or equilibrium.
So the previous slide.
Yes beta.
So the previous.
Okay beta. ये था या ये था, एक सेकेंड, दिस वाज
Thank
okay. Next, equilibrium. Equilibrium. लिखिए बेटा. A system is said to be in equilibrium. A system is said to be in equilibrium if net force. A system is said to be in equilibrium if net force acting on the system is zero. If resultant or net force acting on the system is zero. A system is said to be in equilibrium if resultant or net force acting on the system is zero. I'm talking about translational equilibrium here. So don't confuse.
So net
Here
force.
I'm just talking about translational equilibrium.
So net force की बात क्या था?
A system is said to be in equilibrium if resultant force or net force acting on a system is zero.
Sir, please repeat.
A system is said to be in equilibrium. A system is said to be in equilibrium if resultant force or net force acting on the system is zero. If net force or resultant force acting on it is zero. ठीक है. For conservative system, so if you want to write, you can write. Conservative systems are those systems. Please write. Side में लिख लो आप. Conservative systems are those systems which consist of only conservative force. Which consists of only conservative forces. Conservative systems are those systems which consist of only conservative forces. So for conservative system, how you define force? Force is defined by minus del U by del R. You are going to define like this. And you are saying in equilibrium, it will be zero. It will be zero. Okay? So you are saying, so in equilibrium, in case of equilibrium, it will be. Or even you can write it in terms of x. I'm saying 1D case I'm considering. So you can write del U by del x. Del U by del x is zero. So what will be the condition of equilibrium for the conservative system? For conservative system, condition of equilibrium will be del U or du. If this is 1D problem, you can also write du by dx. If this will be the condition of equilibrium. So if you want to find out equilibrium points, If you want to find out equilibrium points, what you are going to do, you will do this du by dx and equate it to 0. So by solving this equation, you can find out values of x naught. You will find out some values of x, like it may be x naught, it may be x naught 1, and these points, there may be 3 or 4. There may be 2, 3, 4, like this. So they are called as equilibrium points. They are called as equilibrium points. What you call? You call them equilibrium points. Equilibrium points. So at these points, basically net force acting on the system is 0. That's why they are equilibrium points. They are equilibrium points because they are satisfying this condition. And if du by dx or del u by del x is 0, it means at these points, net force acting on the system, they are equal to 0. Net force will become 0. So this is the condition of equilibrium, and by using this equation, you can always find out equilibrium points. Equilibrium points. Now, if I plot a graph between u and x, try to understand. If I plot a graph between u and x, then this condition can be satisfied in two situations. Okay? This condition is going to be satisfied in 2 or 3 situations. Third situation, neutral equilibrium, I'm not going to discuss here. I'm just focusing on stable and unstable equilibrium. So if you plot u as a function of x, and I'm choosing an arbitrary curve like this, it may be like this. I'm considering this type of arbitrary curve. It may be. Here, this is 0, suppose. So can you tell me at which points this du by dx will be 0? At 2 points. One point will be this. In this graph, here, if you draw the tangent, then slope of the tangent will be 0. What is this du by dx? This is the slope. This is representing the slope. So slope is here. At this point, slope will be 0. So one of the equilibrium point will be here. Here, I call it as R naught. R naught. What is this? This is localized minima. So what is this? This is localized minima. This is localized minima. So at the position of localized minima, this equilibrium condition is satisfied. And later on, I will show you this is called as stable equilibrium point. At the position of this minima, we will have why it is stable equilibrium point, I will explain you. So at this point, we are getting at the position of this localized minima, we are getting a equilibrium point, and we call it as stable equilibrium point. Stable equilibrium point. Stable equilibrium point. So just by observing this plot, I can observe that there are 2 points where slope is becoming 0. So one point is this. So here this point at r equal to r0, when particle is at r equal to r0, net force acting on this system will be 0. So that's why this is called as stable equilibrium point. So what I'm saying, if you are placing a particle here, if you place a particle here in this field, potential will be due to some type of field. So if you place a particle here, okay, and it is at rest, then it will remain at rest for infinite time, unless and until you are not disturbing it. This equilibrium point, net force acting on it is 0. 0. So what is going to happen here? Okay, basically particle will remain at rest. Kinetic energy will be 0. If you place it at rest, it will remain at rest. Second point is this, that is localized maxima. What is this? This is localized maxima. I'm not saying the maxima of this curve will be here at this point. No, localized. This is a localized maximum. Maxima will be somewhere. It is increasing like this. So maxima can be anywhere. But here you are getting a peak. This type of peak, they are called as localized maximas. This type of dip is there. I'm not saying this function is minimum here. I'm saying localized minima is here. Minimum value of this function will be somewhere here. So this is localized minima, localized maxima. So this I called it as R01. R01. This is localized maxima. This is called as localized maxima. And even at localized maxima, condition of equilibrium is satisfied. So automatically if you place a particle here with zero kinetic energy, then it will remain at rest for infinite time. Because net force is zero. It should be at rest. Okay? Unless and until you are not disturbing them. And if you are disturbing them, their behavior will be totally different. If you disturb this particle, its behavior will be quite different as compared to the behavior of this particle if it is disturbed. So this is a localized maxima. And localized maxima will be this point, it will be corresponding to, we will call it as unstable. Why unstable? I will explain you. This is called as unstable equilibrium point. Equilibrium point. This will be. So basically you can find out localized maximas and localized minima. Localized minimas will be corresponding to stable equilibrium point and localized maxima will be corresponding to unstable equilibrium point. ठीक है, please write. If we plot potential energy, please write. If we plot potential energy as a function of x, then we will find out localized maximas and localized minimas. We will find out localized maximas and localized minimas. Full stop. These localized maximas will be corresponding to stable equilibrium point. These localized minimas, please write, these localized minimas will be corresponding to stable equilibrium points. And these localized maximas will be corresponding to unstable equilibrium point. So can you tell me the condition of stable equilibrium point from here? You are saying that at R equal to R naught, you are getting a stable equilibrium point. Can you find out some condition mathematically that this will be the condition of, suppose this is the condition of, I write this du by dx. From this condition, I am saying.
Derivative of the potential energy should be maximum.
Okay, beta. So what I am saying here, from this condition du by dx, that will be 0.
Potential energy increases from this point, sir.
Okay. So this is the condition of equilibrium point. Equilibrium points. So from here I find out two equilibrium points. I find out x equal to x naught, suppose, and x equal to x naught 1. One is corresponding to minima. Minima point corresponding to minima is called as stable equilibrium point. And stable equilibrium point is corresponding to localized minima. So you are saying that x equal to x naught, this x naught, this is stable equilibrium point. And it is corresponding to localized minima. So what will be the condition of this localized minima? That will be d, second derivative of this d square u by dx square. This is second derivative. ठीक है ना? This is second derivative. And this will be at x equal to x naught. This will be कितना होगा? This will be greater than 0. This will be greater than 0. So second derivative of this u with respect to x will be positive. Because this is the condition of minima. So localized minima is going to satisfy this condition. So condition for stable equilibrium point will be this. So stable equilibrium points, you are finding them at the position of localized minima. So condition of localized minima will be the condition of stable equilibrium point. So from
Sir,
here, by du by dx equating 0, you can find out equilibrium point. And if you find out its next derivative, second derivative, then the point at which, the equilibrium point at which the second derivative is positive, that will be the condition of localized minima. And we call that point as stable equilibrium point. And this x0, 1, we are calling it as unstable equilibrium point, because it is
Here, sir, are the
corresponding.
2 points are here.
Yes,
X
beta.
equals to x0 and x equals to x01. So if
Yes.
the x equals to 0, derivative of x equals to x0, then there is another local minima point are here.
Yes, there is a local minimum point here. So I will apply. Okay, I know from this graph, this is a minima here. This is, so I can apply the condition of minima. So this is the condition of a stable equilibrium point. And you are going to get a localized maxima at unstable equilibrium point. So condition of maxima will be the condition of unstable equilibrium point. And what it will be, that this d square u by dx square at x equal to x0 1, that should be कितना होना चाहिए, this should be less than 0, negative होना चाहिए, this should be negative. So second derivative will be negative for this unstable equilibrium point, and it will be positive for stable equilibrium point. So in this way, if expression of u is given, you can always find out equilibrium points, and from the equilibrium points you can always find out which equilibrium point is stable equilibrium point and which one will be the unstable equilibrium point. So mathematically you can do this. Now our next question will be why we are saying that this is stable equilibrium point, this is unstable equilibrium point. Okay, mathematically I write the condition, that's okay. But now I will explain you why this is stable, why this is unstable equilibrium point. ठीक है बेटा? So for today I am going to stop here. In the next class I will complete this topic, stability
Sir, I have a
analysis, and
question,
then I
sir.
will discuss numerical problems with of this.
Sir, I have a question, sir. These topics are related to non-linear and the linear. No, sir.
No,
What are
non-linear problems are not in your syllabus.
No,
ठीक है
sir.
ना? If you're talking about
Non-uniform and the uniform circular motions. These topics are about, sir. Now, these topics are related to which classical mechanics also, but
actually this problem is related to the central force problem.
central force.
This is very much actually this topic will be utilized. It should be known well if you want to draw the phase trajectories. ठीक है?
These
Second thing
topics
is
comes from IIT JAM also.
okay. This is a part of IIT JAM also. ठीक है? You will find out 4 or 5 questions in previous year in IIT JAM. You will find out 6, 7 or more than in NET comes at least 20-25 questions you will find out in NET examination. 4 or 5 questions in IIT JAM they have asked in previous year question. In GATE you will find out numerous questions from here. So this is a very I cannot say this is very important topic for IIT JAM, but you will find out it is a very regular in case of NET also. So I will share all the questions with you which are asked in different exams related to this topic, stability analysis, and then I will discuss at least 10-15 questions with you.
सर
So yes beta, please.
सर जिस लेक्चर में आपने यूनिफॉर्म सर्कुलर मोशन के क्वेश्चन डिस्कस किए थे वो लेक्चर गूगल क्लासरूम में अपलोड नहीं हुआ है.
Okay, I will talk to Satyendra ji or Parsuram ji. Actually, I am not aware about that, but I will tell him to upload.
सर मैसेज किया था सर को पर वो अभी तक हुआ नहीं है.
ओके, एक बार मैं बोल दूंगा तो शायद हो जाए. ठीक है, ट्राई करते हैं.
ठीक है सर, थैंक यू सर.
ठीक है ना बेटा, वेलकम.
Thank
also sir,
यस बेटा.
जो सर्कुलर मोशन के जो क्वेश्चंस की जो शीट है सर, उसके सॉल्यूशंस आप देने वाले थे वो मिले
नहीं,
नहीं.
मैं उसके बाकी क्वेश्चन डिस्कस करने वाला हूँ. ठीक है ना. आई विल हैव वन क्लास. ठीक है, for those questions. The questions, some of the questions I have discussed, Rest of the questions I am going to discuss. I will discuss in the class.
सर
Most of the questions.
Okay,
Yes,
thank
beta,
you.
please.
सर मैंने नोटिस किया है कि कुछ लोगों के लिए जैसे हम लोग के लिए ये मतलब फर्स्ट लेक्चर है या सेकेंड या थर्ड लेक्चर है, तो इसके पहले हमें कौन से टॉपिक्स कवर करने हैं जो हमारे नहीं
कुछ
हुए
नहीं
हैं?
करना बेटा. Are you able to understand these two lectures?
Yes, yes, sir, absolutely.
Good, very good. No need to cover anything. I will, if you are joining here from this topic, then I will explain you each and every aspect that is required in the class itself.
सर
Whatever topics are left for you, I'm going to discuss those topics again with you later on.
Thank you, sir.
सर
Welcome. Beta. Yes, beta, please.
सर मेरे पोलर कोऑर्डिनेट्स के सर लेक्चर्स मिस हो गए हैं पहले के ना, तो
I think those lectures are there on YouTube also.
हाँ सर, रिकॉर्डिंग तो है, पर
Okay.
सर मैं पूछ रहा था कि मतलब ये रिलेटेड है उससे.
Polar coordinates are used in circular motion questions, as well as polar coordinates are, to some extent, they are used in central force problem. But
तब
whatever use will be there, if you will have any problem, I even can discuss that point at that place itself.
मतलब सर मैं
You will not find out any problem.
स्टेबिलिटी से कंटिन्यू करूं सर?
हाँ, sure, 100%. Don't look at the old lectures, just start from the stability analysis.
Okay,
Sir,
sir, thank you,
stability
thank you.
analysis, central force, same sir, same topic. Then after central force, after stability analysis,
After stability, I will discuss phase trajectories, because phase trajectories are also needed in central force problem.
this part also forms central force part.
No,
Step.
this is not a central force problem. This is a journal discussion. It will be utilized, these concepts will be utilized in central force problem, but this is a very generalized topic. Okay? It's not only confined to central force problem, it will be applicable at all the places where conservative forces are there. Wherever you are dealing with conservative systems, this will be applicable everywhere.
Sir?
Yes, beta.
Sir, while preparing for ITGM,
Okay.
what percent, in percentage wise, how much syllabus is overlapped with CSI and NET exam?
देखो, I can answer this question tomorrow. ठीक है? I will answer your question tomorrow. I will exactly classify what is common. But if you look at this, your total Newtonian mechanics is different. ठीक है? Newtonian mechanics will be quite different, but I will suggest students from NET, they can also attend. They can learn something good.
Sir,
but
I'm
that is
asking
only
for
for
whole
JAM
syllabus.
student. Yes, please.
Sir, I'm asking for whole syllabus.
For?
Whole syllabus, complete syllabus.
I will explain you tomorrow what is the syllabus of IIT JAM mechanics, ठीक है? As well as for NET students, GATE students. I will classify exactly what we will discuss for IIT JAM and what will be for NET and how we are going to proceed. I will explain you each and every point in the next class. ठीक है? अगर मैं भूल जाऊं मुझे याद दिला देना. ठीक है? At the start of the class.
सर वो आपने सर्कुलर मोशन के जो प्रॉब्लम्स थे उसमें सर आपने एक पीडीएफ सेंड करना था एलिप्स हाइपरबोला और पैराबोला की इक्वेशंस का सर, वो आइडेंटिफाई
PDF
करें
सेंड
हम
करना था
इक्वेशंस
मुझे.
को.
Oh, so you have said that you will cover
आपने
that
बताया
in
था कि आपने
lecture.
बोला था कि आप पीडीएफ
PDF तो मैंने क्वेश्चन शेयर कर दिए थे आपसे सारे. और इफ आई एम नॉट रॉन्ग मैंने पोलर का भी क्वेश्चन शेयर किया और सर्कुलर मोशन का भी किया. सम ऑफ द क्वेश्चंस रिलेटेड टू सर्कुलर मोशन आई हैव नॉट डिस्कस्ड. आई विल डिस्कस दोज क्वेश्चंस इन द क्लास. शायद इफ आई एम नॉट रॉन्ग मैंने बोला हुआ कि मैं टिक करके ना कि विच वन इज करेक्ट विच वन इज रॉन्ग. ठीक है? आई विल शेयर सम PDF विद यू, बट लेटर ऑन आई थिंक I should discuss those questions with you. Otherwise, it will be difficult for many students to solve the questions, or it will be difficult for me to take individual doubts. So it's better to discuss most of the questions in the class. ठीक है बेटा? I will have a class for these questions. चलिए बेटा. Thank you very much.
Thank you, sir.
Next, welcome.
Thank
बेटा.
you, sir.
Welcome बेटा.